Welcome to the pre-recording of the first half of lecture 19, scheduled for the middle of week 7 in our 8-week summer course, our first course on computer algorithms. So today we're going to introduce the notion of NP-completeness. So last time we defined the concept of polynomial time reduction, how one problem can be reduced in polynomial time to another problem. We also indicated the relationships between various problems. For example, the tree satisfiability problem can be reduced to a problem of computing the independent set in a graph. The tree satisfiability problem will come back in the second half of this lecture, where we show that this problem is NP complete. Okay, what does it mean to be NP complete? Let us first look at how we are computing and verifying solutions. So here is the independent set problem. Given a graph, and we say that a subset of the set of vertices is independent. If for any two elements of that set, there is no edge between those two. So the independent set problem gives you a graph and a number and asks, is there an independent set of size of that given number? Typically, we formulate our problems as decision problems because they're easier to work with. We've shown that if you work with polynomial time reducibility, that this can be reduced also to an optimization problem. Find the largest independent set. Well, this is a hard problem, but nevertheless, it's not entirely hopeless. If somebody comes up with an independent set of a certain size, then actually the verification that that graph that we have indeed an independent set of that size is fairly straightforward. So computing, answering this question is rather hard, but verification is rather straightforward. Our second problem was the satisfiability problem, which in general, which is a general problem, but that can be reduced to the tree satisfiability problem, where we have a set of clauses. Every clause consists of exactly 3 terms. And the terms in those clauses are combined with ORs. So then we ask ourselves, is there a truth assignment? Can you assign zeros and ones to the variables so that all the clauses are true? Again, the brute force would enumerate all possible 2 to the power n combinations. So there is actually not really such a great way out of it. But the good thing about this problem is that if somebody gives you a sequence of n bits, that then you can evaluate all those clauses and verify that indeed whether you evaluate to 1, that's what it means to have an instance, a truth assignment that makes it satisfiable. So the question in general is that, is there, among all the 2 to the power n possible choices, is there an assignment of the variables that computes to 1? That's a hard problem, but the good thing is that if somebody comes up with a truth assignment, you just have to evaluate the expression. And that is straightforward. So we make the distinction between computing a solution to a problem and by verifying whether a given output is indeed a solution. If you can verify efficiently, then you could have potentially start guessing or generating random numbers for the answers. And if you feel lucky, then you may actually get done. So this is a non-deterministic uh, algorithm, and one might even a little bit be wary whether it will actually terminate or not. But it is something that one could try. So, for the problems that we consider, the problems will have an efficient verification. Algorithms, trial and error actually work. It's not entirely hopeless. Okay, so let's formalize things a little bit. We work with decision problems. So, decision problems return yes or no. And they are given on input by a finite string of bits. So the input size is finite, and it is denoted by this S between those vertical short lines. So that's a problem, and a decision problem in particular. An algorithm takes on input a string and returns yes or no. Um, so we then say that the algorithm solves the problem if for all the problem instances for which the answer is yes, also our algorithm returns yes. So the set of the problems is actually identified with the inputs that tell you yes for the problem. And an algorithm will actually, for any problem, make that connection. Now, we are interested in efficient algorithms, and they have a running time that is a polynomial in the size of the input, in the size of that input string, and they terminate, so there is a polynomial in that size, and the algorithm terminates in at most big O of that polynomial evaluated at the input size. So this is what it means to be a polynomial running time, and we say that this algorithm is then also efficient. Okay, what is now the set of problems that for which efficient algorithms exist? Well, that is that set P, P for the polynomial running time. So P is a set of problems for which there exists an algorithm that runs in polynomial time. One can also say that all the problems that are in that set P can be solved efficiently, which means that for an arbitrarily input size, not infinite, but we can let that input size grow and the running time will grow like a polynomial. And typically, if the degree of that polynomial is not that high, that will lead to a predictable and manageable running time. Okay, that's the set P. So far in the previous 6 weeks, in the first 6 weeks of this course, we only considered problems in that class. So we are extending our problems, but still we want to consider only those problems for which we can efficiently verify the answers. So what does it mean to check whether an answer is actually an answer? We need to have the input string, and we need to have the separate certificate string. So the certificate string could be a solution. So in terms of the tree satisfiability problem, it could be that assignment. And that contains then enough evidence that indeed uh, we do have the solution. So what is now an efficient certifier? Well, it's an algorithm that runs in polynomial time in size of the inputs and also in size of our certificate. That actually also implies that the separate certificate string actually must be bounded and also not really exponentially longer than s for every input s. There is then a polynomial such that, and that's actually the second clause, I'm actually running a little bit ahead. So the size of that certifier string should actually bounded by an input, by a polynomial in function of the input size. And the certifier will return yes on every certificate. Um, so an efficient certifier, if the proofs are not too long, will evaluate them. And in some sense, it could be a brute force algorithm. Uh, but again, it should be polynomial time. So brute force within the polynomial time constraints. So it shouldn't be that a that a sophisticated algorithm, by the way, as long as it runs in polynomial time. Okay, the class NP is the class of all problems for which you can have an efficient certifier. So this is weaker. So for a certifier, it must be bounded by a polynomial in the input size. So note that there is a similarity in the definition of the sets. So the set NP is also a set of problems, not so much a set of algorithms. And P collects all the problems for which we have an efficient algorithm. NP collects all the problems for which there is an efficient certifier. So there is a similarity between the two sets, and there are correspondences between them. So in particular, every problem for which there is an efficient algorithm belongs to that set NP. Let's prove this. So what does it mean for a problem to belong to the set P? Well, we do have a polynomial time algorithm. We have to show that if you have a polynomial time algorithm, you also have an efficient certifier. Well, what could that certifier be? Well, it will return the value of the algorithm. Remember that the algorithms, the problems that we are considering, are actually decision problems. So we will simply run the algorithm A again, and well, it runs in polynomial time. And it's now important that we are focusing on decision problems, because what happens is that for any certifier string that we take, we will return yes if the output of our algorithm is yes. Otherwise, we will return no. So we do have a certifier. So that will actually tell whether the output matches the output of our efficient algorithm just by running it again. Okay, now the big question is whether these two sets are the same or not, but let's first look at some examples of efficient certifiers. Here is the independent set problem again, illustrated on our example of the previous lecture. We have a graph of 7 vertices. We have connections between the vertices, certain vertices, And then we ask ourselves, for this example here, is there an independent set of size 4? And indeed, if you look at the example, we have colored 4 green vertices. So that means that these, if you pick any pair of these green vertices, there is no edge between them. How would you check this? Well, it doesn't need to be a sophisticated algorithm. You can actually check for any pair. You pick one vertex, one element of the set S. S is something that somebody gives you. And then you try out all the other possibilities that are different from the vertex you picked, and you check whether they are connected by an edge. So this will run, this terminates obviously because the set is finite, and this will run in quadratic time. So by brute force, it means that it is a very straightforward algorithm as long as it is polynomial time. And a quadratic time algorithm is polynomial time. So our certificate is actually also a string of bits. It are the bit representations of the vertex labels. And that is also polynomial time in the input. So that's another important problem here. These are the two aspects of efficient certifiers. So there is an efficient algorithm that takes into input the input. So that's actually the graph, with suffices that we have the edge list, and our certificate is the set S. Okay, so we have considered the vertex cover problem, and a generalization of this was the set cover problem. So what is the set cover problem? We have a universe given and a collection of subsets. So is there a selection of these subsets so that the union of these subsets covers the entire universe? So one application was that we had software systems that were each covering a certain set of required capabilities. So here in our collection we had 10 capabilities. We found a covering of 3 different software systems. So there is overlap, but you can see that if you take the union of those 3, we do have indeed covered the entire collection of capabilities. Okay, what is the certificate now? The certificate are the indices to the subsets. You can also take the entire subsets. And then you have to make sure that the union, that the certifier also runs in polynomial time. And that consists in taking the union of all the selected subsets. So just adding things together. So there are at most n elements in every subset. So you add them to the accumulator, and at the end you check whether you have the universe. So at the worst case, this could be again quadratic. So just have a very straightforward union operation. We have an efficient certifier, so that means that this problem lies in NP, even though we don't really know if there is an efficient algorithm to solve this problem. We mentioned tree satisfiability. So tree satisfiability takes on input a collection of clauses, but tree satisfiability every clause has exactly 3 terms. Exactly, that means that you don't really have x or x, so you don't have duplicate terms. And we are asking in the tree satisfiability problem, is there a truth assignment so that all these clauses are true? So these clauses are conjugated with the and. As soon as there is one of these clauses that is 0, the entire expression evaluates to 0. Here for the example, you can verify it has a satisfying truth assignment. And the certificate is just a sequence of n bits for the n variable, so it's a short certificate. And we will just evaluate compute modulo 2, doing the negation, the addition, the multiplication, and this can be done all very efficiently. So linearly in the size of your Boolean expression, which represents the conjunction. Okay, time for an exercise. So we have seen that the set packing problem is actually generalizing the independent set problem. So here is the independent set problem. We have a collection of elements and then a collection of subsets. Now we do not want to take the union, but we want to ask of these given subsets and some number k, is there a collection, is there a selection of k of sets, we don't know which of these m ones, so that no two of them intersect? Is there an efficient certifier for the set packing problem? So how would you go about this? Well, you would first state what is the certificate. The certificate is a set of indices, and that is polynomial, is polynomial in size. So it has a polynomial size. We have a finite sequence of numbers, no more than m, and m is actually part of the input dimensions. Then what would be the algorithm that verifies that no two of them start to intersect? So that's perhaps a little bit harder because you could start doing all possible pairs, and that's probably the straightforward approach, and that works. So you take the first set and you check for all the other sets whether they intersect or not. So that's linear. It could be that the sets are rather large, but then you would terminate rather early as well if you are a bit smarter. But you can check them all, and your it will be quadratic in the number of sets multiplied by the number of elements that you can have in every step, because you need to compare all of them. But still, it will be a cubic time algorithm, and that is polynomial time. So we do have an efficient algorithm for the set packing problem. So efficient here, in the light of problems that may require an exponential time, is indeed relevant, is relative. So checking all possible combinations in the first half of the course, we've seen that you can actually often reduce this to n log n to subquadratic time. Here for the efficient certifier, it doesn't really matter. So in some sense, we relax things a little bit. Okay, now this is the big question, and it's mainly important in this course that one understands the relevance, why this is such a important question, which has not been proven, although the general understanding and belief is that polynomial time is not equal to non-deterministic polynomial time. I should have probably pointed this out with the trial and error algorithm. So NP is also the class of the set of problems for which there is an efficient um, certifier, is also called the non-deterministic polynomial time, because you can always guess and generate random numbers. Okay, why is it not the case? Because there are so many thousands and thousands of NP-complete problems. So many different problems for which nobody has yet found an efficient algorithm. And all these problems are related because they are NP-complete. Many problems are reduced to them. So the fact that nobody has yet come up with, say, an efficient problem which would collapse everything, that means that there is indeed strong, I wouldn't say evidence, but strong belief that these two are different. Okay, let's now define what does NP completeness mean. And in some sense, why is it important to know how hard certain problems are? So what is an complete problem? It's complete in the sense that all problems in the class can be reduced to polynomial in polynomial time. So they are polynomial time reducible to that NP complete problem. So what does this mean? If x would be, so since all the other problems are reducible to that NP complete problem, as soon as you would have a black box solver for x, you could take the input of any problem that polynomial time reduces to it, and you could also solve it efficiently with the black box that you have for x. Then that would mean that the class of undeterministic polynomial time problems, the NP, the set of NP, would actually collapse onto the set of problems for which we have efficient algorithms. So that is the importance of being NP complete. And we can prove this theorem. So we say that, and that's actually a good proof because it emphasizes, it reinforces the definition of NP complete. So what does it mean to be NP complete? Well, suppose that P would equal to NP, then it would actually mean that that NP complete problem would be solved in polynomial time. So that's the easy direction from right to left. Suppose now that x can be solved in polynomial time. That it is an NP complete problem implies that all problems in the set NP can be reduced in polynomial time to an instance of that problem x, to an input, and then it can be solved. And since we are working with decision problems, it's yes or no. So so that's what it means to be polynomial time reducible. So if x can be solved in polynomial time, then y can be solved in polynomial time. So any other problem would actually belong to, in the class NP, would actually belong to also the class P. We've just proven the other way, the other inclusion. So if we have an efficient algorithm, we have an efficient certifier. We constructed one. So therefore, if you can solve an NP-complete problem and any NP-complete problem in polynomial time, then actually P equals NP. Okay, here again, why NP complete problems are important. So if we have an NP complete problem, then that's the theorem again. So if you could show, on the other hand, that you have an NP complete problem and you could demonstrate that there can't be any efficient algorithm for it, there can't be any algorithm that solves it and runs in polynomial time, then no NP complete problem can be solved in polynomial time. Okay, in the second half of this lecture, we will demonstrate that NP-complete problems exist. So that is a little bit harder than what we did in the previous lecture by reformulating a specific problem in polynomial time. So we actually, for NP completeness, we actually want to encode any problem. So to make sure that any, so what is actually the structure that we would use, the techniques that we would use to encode any problem in that set NP. Okay, we will do that for the tree satisfiability problem in the second half of this lecture, which is the next pre-recording.